I would like to talk about the capacitor with a dielectric. What is a dielectric, man? Remember, if you remember the first class, every time you have like any material between the plates of a capacitor, so this material is called a dielectric. So this is dielectric is actually used to increase the capacitance of the capacitor. We can actually see this. You guys are. Let's use this simulation from from the University of Colorado, right? You have the for example, for this capacitor here, so we have a parallel plate capacitor, and the plate area is 100 square millimeters, and the separation is 5 millimeters. For this capacitor, considering that the vacuum, this is a vacuum capacitor, right? The capacitance here is 0.18 times 10 to minus 12 farad. If I put a dielectric here, as you can see, the capacitance here increased, and increased proportionally to the dielectric constant that we call K. So everything that happens actually, we don't have to calculate, we don't have to find extra expressions. What I'm saying is that we don't have to find extra expressions to calculate the like a new capacitance for every kind of capacitor if you just input like a dielectric. All you have to do, guys, is actually multiply this capacitance by the dielectric constant K. That's all you have to do, because the expressions are going to be exactly the same. Remember that, for example, we derived the expressions for the parallel plate capacitor, right? It was always the capacitance was always the permittivity of the free space multiplied by 1 unit of length, right? So that's the main point here. For a capacitor with a dielectric, this is still true. The only thing that you have to do actually is think that you are only multiplying now. The same expression that you have for the vacuum capacitor, you just have to multiply this dielectric constant, include in the expression, and then you have exactly the same. You calculate and you have one expression that is just proportional to the one of the vacuum capacitor. That is actually explicit here. Right? We found that the capacitance for a capacitor using just air or vacuum, right, was just the permittivity multiplied by some kind of length. If you, what do you do for a capacitor with a dielectric is that you just multiply this constant, and that means, well, the consequence here that the capacitance of a capacitor with a dielectric is proportional to the one with the regular capacitor, right? The vacuum capacitor, let's say. That's the conclusion here. It is not my conclusion. Who had this brilliant idea was Faraday. Always Michael. Michael, guy, amazing. So many surprises. Magnetism. And then it's very easy. All you have to do is just actually include this dielectric constant in all these expressions, and then everything we have been doing regarding capacitors is valid. We don't have like a different mathematics or more complicated um, expressions to represent the behavior of the electronic components. Okay, guys. So just to finish this part, I'm going to show you some basic, some typical values for this constant K. Look, the air, we already know, right? This is about 1. Generally, we approximate as 1. Is very, very close to the vacuum, to the free space. Going to be 1, very close. And for most practical applications, we will just round off this as 1. And you have some other materials. If you guys grab one capacitor and you guys dismantle a capacitor, you guys going to see that you have the dielectric inside. And for example, paper, you have like 3.5. See, you can actually increase the capacitance of a capacitor like 3.5 times just by inserting like a piece of paper inside. And you have, like, for example, transformer oil 4.5. I don't know what is the most popular like dielectric for capacitors. Actually, if you guys know, please let me know. I'm not sure, but you have some very big values sometimes. Strontium titanate, what the hell is that? Strontium and titanium? No idea. How about you guys? We have some chemists in the class. If you guys know, no idea, not sure. But my point here for this class is very simple. Just have to multiply by the dielectric constant to calculate the capacitances. The capacitor with any dielectric. Okay, guys, this is all now. And then to finish, I would like to solve one problem for that with time, and I'm going to solve this problem. Right, this is the problem 49 from our textbook. And that's not typical, right? So we don't solve this kind of problems in high school, so that's why I chose this problem. Where is it? So let's read this problem. So we have this figure here is showing, like, is illustrating like a parallel plate capacitor with a given area A, right, in a given separation D, but we have two different materials here. The top part is one material with a dielectric constant K2, and the top part is a dielectric constant K1. So how to do this? And why I cannot lines? I need lines. Kind of paranoid about. Okay. First of all, okay, let's assume, guys, like always, right? Let's assume that one plate has a positive charge. I'm choosing, for example, doesn't matter exactly. Let's put in red. I'm considering the top plate going to be a positive charge. Bottom plate is going to be a negative charge. Then I can write the two electric fields for this, considering only the top plate is going to be. Remember, we know this already, right? This is going to be K K1 epsilon A, right? And you can write the electric field the other plate for the negative. Sorry, this is the bottom plate, top plate. Have the same areas. Okay, we know we can write actually this the voltage, the potential difference there going to be this uniform field, right? I'm considering uniform field. For example, with this part here, and then uniform field part here. This, and then the uniform, and you know the expression for uniform fields. This is going to be the product, the electric intensity of the electric field times the distance, right? Going to be 2 plus dollars. They're going to sum up. Going to be E2. You can substitute here these two equations right here. Get in. I prefer one. Can substitute one here. Doing this here, here. Going to give me AD for 2 epsilon 0A. And then we have here for the product, these two guys, the electric constants. 1, 2. And we know that the capacitance, all you have to do divide by A divided by this current of current potential. This is going to give me epsilon 0 A per D E by 2 denominator product. Whoa, what is the significance of what you just found? Well, we can see here, guys, that actually this is exactly the same expression that we found for the equivalent capacitor in series, right? Remember, if you go back, if you have two capacitors in series right here, series, look, it's going to be exactly the same, like you have two capacitors. And for the case, look, and for the case, that's a not significance of what we just found. If you have only one, right? You have only one material here. That means that the K1 equal to K2. So this is going to give us exactly the same expression we found for the parallel plate capacitor. Aha, very interesting. And in this case, yeah, exactly the same. Where's the I? Exactly the same. Yeah, well, that's all I would like to say.